Okay, so we are going to start on lesson 29. So you should have had a quiz before this lecture started, and it would have been over lesson 28 material. Okay, so today we have a little bit more of the ideal gas laws to go over. But we're going to finish the individual gas laws and then start moving into talking about the ideal gas law, which is kind of like the big kahuna of this chapter is the ideal gas law. Okay, so we already talked about this question, which is Avogadro's law. And then this asks us to take all of them together and all of the individual ones we talked about, Mott's, Charles, Boyle's, and Avogadro's, and combine it into the ideal gas equation. And that looks like this. Okay, so we have pressure times volume is equal to the number of moles times the ideal gas constant times the temperature. Okay, so we're going to wait on the units simply because the next one's going to kind of force us to think about the units. So there are two versions of R that we use for what I call PIV-NERT, and that's pretty common. You'll hear people say use PIV-NERT. That's PV equals NRT, PIV-NERT. So the two most common versions of R are 0.08206, and this is units of liters times atmospheres divided by moles times Kelvin. So here you can see clearly the units. Okay. The units of pressure in this case are atmosphere, volume is liters, moles is moles, and temperature is Kelvin. So the ideal gas constant that you use will dictate what the units of pressure, volume, moles, and temperature may be. The other version of the ideal gas constant that gets used a little bit less is 8.314, and the units are kilopascals times liters divided by moles times Kelvin. So you'll see the only difference between these two are that the units of pressure are different. Okay, so you need to know this. You need to know the ideal gas constant R, you need to know the value, and then the units. So what is meant by an ideal gas? This is important because we're going to talk about non-ideal in a few lessons. And ideal gas law is that it's going to behave as expected. And this is kind of also loosely thought of as, in theory, this is what should happen. Okay, and we assume this is true under what we call ideal conditions. But in reality, we're going to see that gases don't behave as expected. They don't behave in theory. And some of it's because of their non-ideal conditions, and other of it is because of some other aspects of gases that we're going to see with the kinetic molecular theory. Okay, but normally you'll hear a question will say under ideal conditions or an ideal gas, and so then you can usually apply PIV-NERT, Boyle's law, Charles's law, Mott's, and Avogadro's law. Now, there is kind of an in-between of what's called the ideal gas law. So it's taking two of the individual gas laws and combining them. So maybe it's three. You can think of it in multiple ways. But this is the combined gas law. So it combines pressure, volume, and temperature. And, pressure and volume are inversely related. That's still true here. Pressure and temperature, as well as volume and temperature, were directly related. That's still true here. The only thing is that this is where N is constant. So instead of having two constants and two variables like we did before, we have three variables and one constant. So this is kind of an in-between of the ideal gas law. Because if we rearrange the ideal gas law, Okay, so I'm just taking this and rearranging it. If N is constant and R is constant, then this side theoretically could be canceled out, and that's how we get one set of conditions that we can compare to another set of conditions. Okay. All right, standard temperature and pressure, often just referred to as STP, is a set of experimental conditions. So experimental conditions are pressure, temperature, things like that we can control experimentally. Think of like a lab. And this says what is temperature, pressure, and volume at STP. Okay? And these are values that you need to know. So at standard temperature, we're talking about 273.15 Kelvin. Pressure is 1 atmosphere, so sea level. And the standard volume is 22.4 liters. Okay? So these are the experimental conditions at STP. And then Dalton's law of partial pressures, you can very easily look up this definition. If you're unsure, at the very end there should be time to ask the person next to you or to ask the instructor that is there with you today. All right, so let's practice some math. Okay, chapter 9, because we've done a lot of formulas, you can see it's going to be a lot of math, but there are definitely a lot of concepts, and I think we spent some time last time going over concepts. So today we will focus primarily on the math. So the question that we have here says the volume of an automobile airbag was 66.8 liters when inflated at 25 degrees Celsius with a mass of 77.8 grams of nitrogen gas. So remember, this is a diatomic, meaning it does not exist by itself as a lone nitrogen. It's going to find another nitrogen and pair up and make nitrogen into gas. And it wants to know what is the pressure in the bag in kilopascals. So I can see here that I have volume, temperature, and I need pressure. I don't have another set of conditions, so I'm not looking at using Avogadro's, Amontons, Charles Boyle's, or combined gas law because I don't have a before and an after. So I'm going to use ideal gas law. And it may not look to you like it's very clear right now, but the thing is I have a mass, and I know what my mass is of. It's of nitrogen. And so if you think back to chapter 3, we spent a lot of time talking about how to go from masses to moles, which will give us this value right here. Okay? So we have 77.8 grams of nitrogen. Let me go ahead and specify that. And I know that nitrogen weighs, each one's about 14 grams per mole. So if I have 2 of them, the molar mass is 28 grams of nitrogen for every 1 mole of nitrogen. And I'm going to go ahead and leave this. No, let me go get my calculator. I didn't solve for this one on my paper. So now we're going to take 77.8 and we're going to divide it by 28. And this will give us the number of moles. Should be a number greater than 1. Helps me make sure we get the right answer. And that is going to be 2.78 moles of N2. So now at this point, I have everything I need to plug in. Sometimes with Pivnert, I like to rearrange it first, the formula, to solve for the variable I'm looking for, because it means I'm less likely to make a mistake. Okay, so I need pressure. I've solved for pressure. It's correct. And now I'm going to plug in my values. 2.78 moles. Now, it's an important decision about R because it tells me that I need to solve for kilopascals, so I can go ahead and use the second R constant because that gives me units of kilopascals. Okay, and now I'm going to multiply by the temperature. Temperature was given to me in Celsius, but I need it in Kelvin. So I'm going to go ahead and convert that right above where I'm going to plug it in. And then my liters, that's the correct units to cancel out with my ideal gas. So moles and moles, liters and liters, Kelvin and Kelvin, which will leave me units of kilopascals, which will answer my question. And so the final answer here is 103 kilopascals. Okay. Now, if you look at the book, it does give you another formula where it combines mass and molar mass in an ideal gas equation, but you don't have to memorize a whole new one. You just have to apply something we've already seen, which is stoichiometry, to now apply to ideal gas. All right. Next one says, how many grams of a gas are present in a volume of 0.100 liters of carbon dioxide at a pressure of 307 torr and a temperature of 26 degrees Celsius? So it's working backwards from what I just did. So in this case, I now need to solve for number of moles. However, I have some variables that I need to convert to the correct units first. So pressure is 307 torr. I either need to convert it to atmospheres or kilopascals. I prefer atmospheres because I know that ideal gas constant a lot better. It's more familiar to me. So I'm going to go ahead and convert the torr by dividing by 760, which will give me that pressure in atmospheres. Okay, so 0.404 atmospheres. And then let's go ahead and convert the Celsius to Kelvin. And that's going to be 299 Kelvin. So everything else should be good. Volume is good. So now I'm going to rearrange my Pivnert equation to solve for number of moles. And we tend to get kind of sloppy about this and end up dividing on the wrong sides, which is why I like to do it before I start. So now I have my pressure. I have my volume. I'm going to use my 0.08206 version of the R because I'm in atmospheres. And then my temperature is 299 Kelvin. So now units, I always like to make sure that these are canceling out, which will leave me with moles. It doesn't matter that it's on the denominator, in the denominator, because now it's going to become the numerator when I divide out the problem. So this is going to give me 0.001605 moles of carbon dioxide. But that doesn't answer my question. It needs mass. So I'm going to end with this opposite of the first step on the last problem, which is converting from moles to grams instead of grams to moles. So 1 mole of carbon dioxide, we have 12 plus 32 for oxygen, which gives me 44 grams of carbon dioxide for every 1 mole of carbon dioxide. So when I multiply that across, I get 0.0726 grams of carbon dioxide. Okay. All right. Next one says how many grams of gas are present in 8.75 liters. So volume of ethane. Actually, that's probably ethylene gas at this pressure, at this temperature. So in this case, my kilopascals are really the only ones that aren't in the correct units, but I still need to know grams, so it's identical to the problem up here. But this time I'm going to use my R constant that's already in kilopascals, so it saves me some conversion. So I have a pressure of 378.3 kilopascals times 8.75 liters. divided by 8.314 kilopascals times liters divided by moles times Kelvin, and then 483 Kelvin. So it's really nice when the units are already in the right units and they just need to cancel out. So when I solve for that, it's going to give me 0.824 moles of C2H4. Molar mass of that is 12 times 2 for the carbon, plus 1 times 4 for the hydrogens, which gives me 28 grams per mole. When I solve for this, it's going to give me 23.1 grams of ethylene. Okay, so you can see how important the Pivnert equation is going to be. All right. The next equation, there are more than one way to approach this. You can use Pivnert and then do a little dimensional analysis, or you can use kind of a derived version. It's just algebraically substituted and rearranged so that we can solve for the density of a gas. Now, density of gases are usually expressed in grams per liter. So this version of the equation is grams per liter, which is really, if we think about it, mass divided by volume. Let me write that on the opposite side. I don't want it to look like it's part of the problem. And it's going to be equal to the pressure times the molar mass. So that swoopy M is the molar mass of the gas. So now I'm going to finish the rest of it. It's of dinitrogen monoxide. So if you don't remember covalent naming, there's the formula at a temperature of this and a pressure of that. So in this equation, now I have everything except for the big swoopy M, the molar mass, but I can very easily calculate that. 14 for nitrogen times 2 plus 16 for the 1 oxygen. It's going to give me a total of 44 grams per mole. So it has the same molar mass as our C2H4 did, our CO2 did up above. Okay, so now I'm just going to plug everything in. My pressure, I'm going to go ahead and leave it at 113 kilopascals, and I'm just going to use the R constant that matches. So now I'm going to have 8.314 kilopascals times liters divided by moles times Kelvin. Multiply that by the temperature I'm given, which is already in Kelvin, so that's great. Now let's see what's going to cancel out. Kilopascals and kilopascals, moles and moles, Kelvin and Kelvin, which will leave me with the units of grams per liter, which I said I needed to express the density of the gas that I'm given in the problem. So multiply on top, divide by the product on the bottom, and you should get 1.84 grams per liter as the density of dinitrogen monoxide. So word to the wise here, on your calculator, if you are really sloppy with your parentheses, which sometimes we are because we assume that the calculator will know order of operations, I would, on problems like this, use extra parentheses when I type into my calculator, okay? And I'll tell you what can happen. If you don't very clearly indicate that these need to be multiplied first before division occurs, what your calculator can sometimes do, and it's a user error, is it breaks up this right here. And instead of multiplying on the bottom, it does this first, then it divides, and then it multiplies by 325. And so it does not take into account the order of operations that you're expecting it to. I didn't mean to change that to blue. Because it's not understanding that this needs to stay together. So you need to figure out, is your calculator one that understands this is happening, or is your calculator doing this? And this is a great opportunity to check that, because if you're not getting the answers that you see here, it's probably because your calculator doesn't understand, because you're not putting enough parentheses. Okay? If you're not sure, you can ask Dr. Spencer, you can ask Dr. Morris, whoever is there with you today, but just realize that we're not all well versed in your calculators, and it may take them a little bit, and you might be better off finding someone who has a calculator like yours and see what they're doing, if they're getting the correct answer. All right, 2 more problems. Okay, these are all going to be kind of different versions. The nice thing is that Sapling Homework is going to have you do quite a few of these. So by the end of this lesson, and hopefully Sapling Homework, you will be well versed. All right, so what is the molar mass of a gas if I have 0.0494 grams, so that's a typo, grams of the gas that occupies a volume of this at a temperature of that and a pressure of that? Okay, so there's a couple of things here. Celsius is not going to fly, and torr is not going to fly. I don't know the identity of my gas, so I can't this time convert to moles. Okay, that's actually what I need to solve for, is the number of moles. So let's convert our pressure and temperature first. Very similar to problem number 2 that we did earlier. In fact, the numbers are the same. At least the numbers of the conversions are the same. Temperature 26 degrees Celsius plus 273 to convert to Kelvin. And now I have everything correctly converted. So you might be asking yourself at this point, am I always going to be solving for number of moles? And that is not the case. It just seems like it because we're doing quite a few of these right here. That is not the case. You will get to solve for more than just number of moles and mass. So we have to remind ourselves why we're using R, this version of R, and it's because the pressure is in atmospheres and we need them to cancel out. And they will not cancel out if we don't have the same units of atmospheres and kilopascals of pressure. So atmospheres, liters, Kelvin. It's going to leave me with the units of moles, which is great because that's what I need. So when I do the math correctly in my calculator, I should get 0.001647 moles. Remember, this is an intermediate answer. It's not the final answer, so it's often better to leave more digits at this point than to round up or round down. And now I'm going to need to solve for molar mass. So we have to think back. Molar mass is floating around. Molar mass is moles of whoever. It's grams, of whoever divided by moles of that same substance. So in this case, the question gave me the mass. The only thing that was wrong was I had to add the units in. It was a typo. And then I solved for the number of moles, right? That was the whole point of Pivner, was to determine how many moles of gas I had in the system. So this will give me an answer of 29.99. But that is 30 grams per mole. That is the molar mass of the gas of our system. Okay. So one of the things that Sapling will have you do is calculate molar mass and then identify who the gas is with the molar mass. Okay, so it's kind of an extra step. In this case, we probably would need a little bit more information to determine identity because there's a lot of options to add 30 together, but I don't know that we would all know what exists as a gas or a liquid or a solid at this stage. But Sapling will have you go an extra step further and identify who. Okay, kind of a multiple choice question you might see where it says like, what is the identity of the gas that has this following information? You would solve for the molar mass and then pick from the multiple choice option the gas that has the same molar mass. Okay, I think there's one on your practice exams like that. All right, last but not least, we are going to do a problem about Dalton's law of partial pressures. Now, Dalton's law of partial pressures, at its simplest form, looks something like this, meaning that the total pressure of the system is equal to the pressure of A plus the pressure of B, and so on and so forth. So if you had 5 gases, it would be the total of each individual pressure of that gas added together to give the total pressure of the system. Okay. In its most complex form, it's going to look like the problem we have here. Okay. Sometimes you're just given this is 1 atmosphere, this is 2 atmospheres, and then you just add them together. However, in this case, we're told that we have a volume of a cylinder of gas, and we know that it's a mixture because it's going to give us some further information, which is that we have 350 grams of carbon dioxide and 805 grams of oxygen and 4,880 grams of nitrogen. We're given a temperature, and we're asked what the total pressure is of the mixture. So because it's asking for the mixture, we have to do Dalton's law of partial pressures. We have to determine the individual pressures of the 3 components and then add them together, which really looks like 3 separate Pivnert equations. Okay, so carbon dioxide. We need to solve for pressure. So we're going to solve for Pivnert like this. Now I need number of moles, an R, a T, and a volume. So the only thing I don't really have right off the bat is how many moles 350 grams of carbon dioxide is. So down here, we'll take 350 grams of CO2. I've already said that its molar mass as above was 44. So this is going to be 7.95 moles. So now I can plug in. I'm going to use, because it does say atmospheres, so let's make sure we get that correct. I'm going to go ahead and use my 0.08206. You're going to see that most of the time you're going to use this version of R. And then my temperature, which is 25 degrees Celsius plus 273, which is 298. Pretty common value. And the volume of my whole cylinder is 36 liters. Okay, so when I solve for this, it tells me that the carbon dioxide has an individual pressure of 5.4 atmospheres. So that's the first value I need. So now I'm going to repeat that. I've done carbon dioxide. Now I'm going to repeat that with oxygen. If I determine how many moles of oxygen this is, it's going to be 805 grams of oxygen, which has a 32 molar mass. And that's going to be 805 divided by 32, which is 25.16 moles. Again, these are intermediate answers, so I'm not worried about the sig figs. When you get to upper level chemistry, if that's your path, battery's getting low, you will learn that we handle intermediate answers a little bit differently. But for now, we get to treat them more simply, which is nice because we're learning a lot of other complex stuff. Plug in the rest of the information. You'll see the only difference between the two is the number of moles. So I solve for this, and I'm going to get that equals 17.1 atmospheres. We would expect that the pressure would be greater for oxygen because I have more oxygen than I do carbon dioxide. All right, nitrogen. So I'm going to set up my other this one's a big number, 4,880 grams is the number of nitrogen mass, or is the mass of nitrogen. 28 is the molar mass. So I'm going to take 4,888 and divide it by 28, which is the molar mass. 174.29 moles. So we should expect the pressure from nitrogen is going to be even greater. Everything else gets to stay the exact same. Don't want to change any of the values at this point because the system is still the same. And this gives me 118.3 atmospheres for nitrogen. So now, Dalton's partial pressure, the final step is that if there are three components with three pressures, which there are, then I need to take their individual pressures and total them together. So now that I've solved for them all, I can determine the total pressure. P total is 140.8 atm. Okay. Sapling will have you walk through several of these problems. Not several, I think maybe two. Okay, it's going to ask you some conceptual information about what Dalton's partial pressure law is. Okay. Again, these YouTube videos are already uploaded for you on Canvas, and so you should be able to go back and watch it, to clean up any of your notes, to hear something again if you weren't quite sure. The most important part of this particular lesson is knowing the Pivnert equation, knowing what Dalton's law, partial pressure law states, and then also knowing how to rearrange these equations cleanly. The best way to do that is to be very diligent with your units. I will grade your exams looking for you to show your work like this. I want to see units. I want to see that they're canceling out, and they need to be in your final answer. Okay? I hope that all is going well for you. You should have some additional time at the end of this lesson now to ask any questions of Dr. Spencer or Dr. Morris, whoever is there with y'all. So that you can clarify anything you're unsure of, and just to check base with a human, you can feel free to email me. At this point, you should be watching this the Wednesday following my surgery, so I should be home hopefully by now, and probably itching to respond to some emails. So I hope all is going good for you at this point this semester, and I look forward to seeing y'all again in the spring.